Forward. Before we start, there are two things I would like to share with you. The first is a promise, the second is an ambition. The promise is that the book contains
Before we start, there are two things I would like to share with you.
Before we start, there are two things I would like to share with you. The first is a promise.
Before we start, there are two things I would like.
Before we start, there are two things I would like to share with you. The first is a promise, the second is an ambition. The promise is that the book contains only one equation. Here it is. E equals mc. The ambition, my ambition, is that in this book I will not leave any readers behind. You are about to start a journey through the universe as it is understood by science today. It is my deepest belief that we can all understand this stuff. And that journey begins a very long way from home, on the other side of the world. Part 1: The Cosmos. 1. A silent boom. Picture yourself on a faraway volcanic island on a warm, cloudless summer night. The surrounding ocean is as still as a lake. Only the tiniest of waves wash against the white sand. All is quiet. You are lying on the beach. Your eyes are closed. The warm, sun-baked sand heats up air saturated with sweet, exotic scents. There is peace all around. A wild shriek in the distance makes you jump and stare into the darkness. Then, nothing. Whatever shrieked is now quiet. There is nothing to be afraid of after all. This island may be dangerous for some creatures, but not for you. You are a human, the mightiest of predators. Your friends will soon be joining you for a drink and you are on holiday, so you lie back on the sand to focus on thoughts worthy of your species. A myriad of tiny lights flickers throughout the vast night sky. Stars. Even with the naked eye you see them everywhere. And you remember questions you had as a child. What are they, these stars? Why do they flicker? How far away are they? And now you wonder, will we ever really know? With a sigh, you relax back on the warm sand and put these silly questions aside, thinking why should we care? A tiny shooting star gently streaks across the sky overhead and, just as you are about to make a wish, the most extraordinary thing happens. As if to answer your last question, 5 billion years suddenly pass and the next thing you know, you are no longer on a beach, but in outer space, floating through emptiness. You can see and hear and feel, but your body is gone. You are ethereal. Pure mind. And you don't even have the time to wonder what just happened or to shout and call for help, for you are in the most peculiar of situations. In front of you, a few 100,000 miles ahead, a ball is flying against a background of tiny distant stars. It glows with a dark orange light, moves towards you, spins. It doesn't take you long to figure out that its surface is covered with molten rocks and that what you are facing is a planet. A liquefied planet. Shocked, a question comes to your mind: what monstrous source of heat could liquefy an entire world like this? But then a star, immense, appears to your right. Its sheer size, compared to that of the planet, is just astounding. And it spins too. And it also moves through space. And it seems to be growing. The planet, although much closer, now looks like a child's tiny orange marble facing a gigantic ball that continues to grow at an astonishing rate. It is already twice the size it was a minute ago. Presently, it has a red hue, and it angrily ejects huge filaments of million-degree hot plasma that blast through space at what seems to be very close to the speed of light. Everything you see is of a monstrous beauty. In fact, you are living through one of the most violent events the universe can provide. And yet there is no sound. All is silence, for sound does not spread in the vacuum of space. Surely the star won't be able to keep growing at this rate, and yet it does. It is now beyond any size you could have imagined, and the liquefied planet, pounded by energies beyond its strength, is blown to nothingness. The star did not even notice. It keeps growing, reaches about 100 times its initial size, and then, quite suddenly, it explodes, firing all the matter it was made of into outer space. A shock wave passes through your ghostly form, and then only dust remains, blown in all directions. The star is no more. It has become a spectacular and colorful cloud that now spreads into the interstellar void at a velocity worthy of gods. Slowly, very slowly, you come back to your senses and, as you realize what just happened, a strange lucidity fills your mind with a fearsome truth. The star that died was not a random star. It was the sun. Our sun. And the molten planet that vanished within its brightness was the Earth. Our planet. Your home. Gone. What you witnessed was the end of our world. Not a speculative end, not a far-fetched fantasy of supposedly Mayan origin. The real one. One that mankind has known would happen since some time before you were born, 5 billion years before what you just saw. As you try to pull these thoughts together, your mind is instantly sent back to the present, inside your body, on the beach again. Your heart races and you sit up and look around, as if waking from a strange dream. The trees, the sand, the sea, and the wind are there. Your friends are on their way. You can see them in the distance. What happened? Did you fall asleep? Did you dream what you saw? An uncanny feeling spreads throughout your body as your queries start to shift. Could it have been real? Will the sun really explode one day? And if so, what will happen to humanity? Can anyone survive such an apocalypse? Will everything up to the very memory of our own existence vanish into cosmic oblivion? Gazing once more up at the starlit skyscape above, you desperately try to make sense of what happened. Deep down, you know that you did not just dream at all. Although your mind is back on your beach, reunited with your body, you know you really did travel beyond your time into a faraway future, to see something no one should ever see. Slowly breathing in and out to calm down, you start hearing strange noises, as if the wind, the waves, the birds and the stars are all whispering a song that only you can hear, and you suddenly understand what they are all singing about. It is both a warning and an invitation. Of all possible futures available, they murmur, only one path will allow humanity to survive the inevitable death of the sun and most other catastrophes. The path of knowledge, of science. A journey open to humans only. A journey that you are about to take. Another wild shriek pierces the night, but you hardly hear it this time. As if a seed just planted in your mind was already starting to sprout, you feel the urge to find out what is known about this universe of yours. Humbly lifting your sight again, you now gaze at the stars with the eyes of a child. What is the universe made of? What lies in the vicinity of the Earth? And beyond? How far can one look? Is anything known about the universe's history? Does it even have one? As the waves gently wash over the shore, as you wonder if one will ever be able to probe these cosmic mysteries, the twinkling of the stars seems to lull your body into a half-conscious state. You can hear your approaching friends' conversations, but, strangely, you already feel the world differently than you did a few minutes ago. Everything seems somehow richer, more profound, as if your mind and body were both part of something much, much bigger than anything you had ever thought of before. Your hands, your legs, your skin. Matter. Time. Space. Intertwined fields of forces all around you. A veil you didn't even know was there has been lifted from the world to reveal a mysterious and unexpected reality. Your mind yearns to be back among the stars, and you have the feeling that some extraordinary journey is about to take you very far away from your home world. To the moon. If you're reading this, it means you've already traveled 5 billion years into the future. A good start, by anyone's standards. So you should be confident that your imagination is working well, and that is perfect, because imagination is all you'll need to travel through space and time and matter and energy, to discover what is known about our reality from an early 21st century perspective. You didn't ask for it, but you did happen to see what fate awaits mankind, indeed all life forms on Earth, if nothing is done to understand how nature works. To survive in the long run, to avoid being swallowed by a furious dying sun, our only chance is to learn how to take our future into our own hands. And for this to happen, we need to unravel the laws of nature itself, and learn how to put them to good use. It's fair to say that we have a lot to get through. In the following pages, however, you shall see pretty much everything that is known so far. Traveling throughout our universe, you will discover what gravity is about and how atoms and particles interact with each other without ever touching each other. You will find out that our universe is mostly made up of mysteries and that these mysteries have led to the introduction of new types of matter and energy. And then, once you've seen everything that is known, you will jump into the unknown and see what some of the brightest theoretical physicists of today are working on to explain the very strange realities we happen to be a part of. Parallel universes, multiverses, and extra dimensions will enter the picture. After that, your eyes will probably be shining with the light of knowledge and wisdom that mankind has been gathering and improving for millennia. But you should prepare yourself. Discoveries made during the past decades have changed everything about what we believe to be true. Our universe is not only unfathomably bigger than expected, it is also immensely more beautiful than any of our ancestors could have imagined. And while we're at it, here is another piece of good news. To have figured out as much as we already have makes us humans different from all the other life forms that have ever lived on Earth. And that is a good thing, for most of the other life forms became extinct. The dinosaurs ruled the surface of our planet for about 200 million years, whereas we have done so for no more than a few 100,000. They had plenty of time to start questioning their environment and figure a few things out. They didn't. And they died. Today we humans could at least hope to detect a threatening asteroid early enough to try to deflect it. So we already have some powers they did not have. It might be unfair to say it, but with hindsight we might thus link the dinosaurs' extinction to their lack of awareness of theoretical physics. For now, you still are on the beach, though, and the memory of the dying sun is still vivid in your mind. You don't have that much insight yet and, to be honest, the twinkling dots that stud the night seem utterly oblivious to your existence. The life and death of earthly species makes no difference to them whatsoever. It appears that time, in outer space, works on scales that your body cannot grasp. The entire existence of a species here on Earth probably lasts no more than a snap of the fingers for such distant shining gods. 300 years ago, one of the most famous and brilliant scientists of all time, British physicist and mathematician Isaac Newton, the man who gave us gravity from Cambridge University, England, actually thought in such terms about time. For him, there was the time of humans, felt by us all and measured by our clocks, and there was the time of God, which is instantaneous, which doesn't flow. From the point of view of Newton's God, the infinite line of human time, stretching backward and forward into infinity, is but an instant. He sees it all in one blink. You are not God, though, and as you watch the stars, as a friend of yours silently pours you a drink, the immensity of the task at hand starts to feel overwhelming. All this is too big, too far away, too strange. Where to begin? You are not a theoretical physicist. But you are not the type to give up either. You have eyes and your mind is curious, so you lie down on the sand and start by focusing on what you can see. The sky is mostly dark. And there are stars. And in between the stars, your naked eye perceives a dim band that glows with a faint whitish light. Whatever this light is, you know the band is called the Milky Way. Its width looks to be about 10 times that of a full moon. You stared at it many times when you were younger, but not that much recently. As you now see it, you realize that it is so conspicuous that it must have been known to your ancestors since forever, and you are right. Ironic to think that, after centuries during which men and women debated its nature, we now know what it is, although light pollution makes it invisible from most inhabited places. From your tropical island, however, its presence is overwhelming and, as the Earth spins as the night advances, the Milky Way moves through the sky, like the sun during the day, from east to west. The possibility that the future of humanity lies somewhere out there, beyond the Earth's sky, starts to become real in your mind, and spellbinding. Focusing, you wonder if it is possible to see all there is in the universe with the naked eye. And then you shake your head. You know that the sun, the moon, some planets like Venus, Mars or Jupiter, some hundreds of stars and that fuzzy streak of whitish dust called the Milky Way don't add up to being everything. There are mysteries hiding up there, out of sight, between the stars, mysteries that are just waiting to be unraveled. If only you could probe it all, what would you do? You would start with the vicinity of the Earth, of course, and then you'd shoot away and go as far as possible, and then your mind obliges. As amazing as it sounds, your mind does start to move away from your body, upwards, towards the stars. A spinning sensation of vertigo hits you as your body, and the island it is lying on, recede rapidly beneath you. Your mind, shaped as an ethereal U, is heading up, and east. How that is even possible, you do not have a clue, but there you are, higher than the tallest of mountains. A very red moon appears, suspended above a distant horizon, and in far less time than it takes to say it, you find yourself out of the Earth's atmosphere, flying across the 380,000 kilometers of emptiness that separate our planet from our only natural satellite. From space, the moon appears as white as the sun. Your journey through knowledge has begun. As only a dozen humans have done before, you've reached the moon. Your ghostly body is now walking on it. The Earth has disappeared below the lunar horizon. You are on its so-called dark side, the side that never sees our planet. There is no blue sky, nor any wind, and not only do you see many more stars above your head than from anywhere on Earth, they don't twinkle. All this because there is no atmosphere on the moon. On lunar soil, space begins a millimeter above the ground. No weather ever erases the scars that scatter its surface. Craters are everywhere, frozen memories of what once hit that barren soil. As you start walking towards the Earth-facing side of the moon, the history of its birth magically pours into your eager mind and you stare, dumbfounded, at the ground beneath your feet. What violence! About 4 billion years ago, our young planet got hit by another one, the size of Mars, which tore a huge chunk of it off into space. During the following millennia, all the debris from that collision settled into a single ball in orbit around our world. When that was done, the moon you are now standing upon was born. Were it to happen today, such a collision would be more than enough to wipe out all life forms on Earth. At the time, though, our world was bare, and it is funny to think that without such a catastrophic bang, we would have no moon to illuminate our nights, no significant tides, and life as we know it probably wouldn't exist on our planet. As the blue Earth appears in front of you, above the lunar horizon, you realize that catastrophic events, on a cosmic scale, can be for the best just as they can be for the worst. Your home planet, seen from out here, is the size of 4 full moons put together. A blue pearl floating in front of a black, star-sprinkled background. Our world's true extent in space is, and will always be, a humbling sight. And as you walk some more and watch it rise in the lunar sky, even though all seems quiet and safe, you already know better than to trust such an apparent peace. Time has another meaning out here, and given the eons that continue to unfold, the universe's violence seems unavoidable. The craters that scar the moon's surface are but a reminder of it. Hundreds of thousands of mountain-sized boulders, adrift in space, must have pounded it over the ages. And they must also have hit the Earth, but our planet's wounds have healed, for our world is alive and hides its past away deep under its ever-changing soil. Still, within such a universe, you suddenly sense that your home world, despite its ability to heal, is fragile, almost defenseless. Almost. But not quite. It now has us. It has you. Collisions such as the one that led to the birth of the moon mostly belong to the past. Today there are no stray planets menacing our world, just loose asteroids and comets, and the moon partly protects and shields us from such hazards. Danger, however, looms everywhere, and, as you watch the Earth's blue-hued image hang in the dark sky, an extraordinarily bright ball of light suddenly rises behind you. You turn around to face a star, the brightest and most violent object that can be found near our home planet. We have named it the Sun. It lies 150 million kilometers away from our world. It is the source of all our power. And as your mind becomes passionately overwhelmed by the sheer amount of light that emanates from this extraordinary cosmic lamp, you leave the moon behind and start flying towards it, our local star, the Sun, to find out why it shines. 3. The Sun. If mankind could, one way or another, harvest all the energy the Sun radiates in 1 second, it would be enough to sustain the entire world's energy needs for about 500 million years. As you fly closer and closer to that star of ours, however, you realize that the Sun is not as big as when you saw it 5 billion years in the future, as it reached its end. Still, it is big. To put things into perspective, if the Sun were the volume of a large watermelon, the tiny Earth would lie some 43 meters away, and you'd need a magnifying glass to see it. You've reached a few thousand miles above the Sun's surface. Behind you, the Earth is but a bright dot. In front of you, the Sun fills half your sky. Bubbles of plasma are erupting all around. Billions of tons of beyond hot matter are ejected right before your eyes and shoot through your ethereal body, as huge, seemingly random loops open up in the Sun's magnetic field. The scenery is extraordinary, to say the least, and, exhilarated by its power, you suddenly wonder what it is that the Earth lacks that makes the Sun so special. What makes a star a star? Where does its energy come from? And why on earth does it have to one day die? To figure this out, you head for the harshest place that can be, the heart of the Sun, more than 500,000 kilometers below its surface. The Earth, by comparison, is about 6,500 kilometers from surface to core. As you jump headfirst into the bright furnace, you remember that all the matter we breathe or see or touch or feel or detect, even the matter your real body contains, is made of atoms. Atoms are the building blocks of everything. They are the Lego bricks of your environment, if you will. Unlike Lego, however, atoms are not rectangular. They are mostly round and consist of a dense, ball-shaped nucleus with tiny, distant electrons swirling around it. Like Lego, however, it is possible to classify atoms by size. The tiniest of them all has been called hydrogen. The second smallest has been named helium. Take these two atoms together, and you have about 98% of all the known matter in the known universe. A lot, certainly, but a smaller proportion than it was in the past. Some 13.8 billion years ago, it is believed these two atoms accounted for near enough 100% of all known matter. Nitrogen, carbon, oxygen, and silver are examples of atoms that can be found today which are not hydrogen nor helium. So they must have appeared later. How? You are on your way to find out. You dive deeper and deeper inside the Sun, the temperature rises and becomes mind-bogglingly hot. As you reach its core, we are talking 16 million degrees Celsius, maybe even more. And there are plenty of hydrogen atoms everywhere. Although they have been stripped naked by the surrounding energy, their electrons are loose, leaving bare nuclei. The pressure is so high, these nuclei are so tightly packed by the weight the whole star exerts on its own heart, that they barely have any freedom to move at all. Instead, they are forced to fuse into one another to become a bigger nucleus. You see it happening right in front of you, a thermonuclear fusion reaction, the creation of big atomic cores out of smaller ones. Once built, as they move out of the furnace that gave them birth, these heavy cores will team up with the lone, free-moving electrons that were stripped away from the hydrogen nuclei, and become new, heavier atoms, nitrogen, carbon, oxygen, silver. For a thermonuclear fusion reaction to occur, a stupendous amount of energy is needed, and that energy is here provided by the sun's crushing gravity, which effectively pulls everything towards its core, thus compressing it immensely. Such a reaction cannot take place naturally on the Earth. Our planet is too small and not dense enough, so its gravity cannot make its core reach the temperature and pressure needed to trigger one. By definition, that is the main difference between a planet and a star. Both are roughly round cosmic objects, but planets are basically small, with rocky cores that are sometimes surrounded by gas. Stars, on the other hand, can be viewed as huge thermonuclear fusion power plants. Their gravitational energy is so big that they are forced by nature to forge matter in their hearts. All the heavy atoms the Earth is made of, all the atoms that are necessary for life, atoms that your body contains, were once forged in the heart of a star. When you breathe, you inhale them. When you touch your skin, or someone else's, you touch stardust. You wondered earlier why stars like the sun had to die and explode at the end of their lives, and here is our answer. Without such endings, there would only be hydrogen and helium around. The matter we are made of would be forever locked within eternal stars. The Earth would not have been born. Life as we know it would simply not exist. To look at this another way, since we are not made out of hydrogen and helium alone, since our bodies and the Earth and everything that surrounds us also contain carbon and oxygen and other atoms, we know that our sun is a second or maybe even third-generation star. 1 or 2 generations of stars had to explode before their dust became the sun, and the Earth, and us. So, what is it that triggered their death? Why are stars doomed to end their shining lives in a spectacular explosion? One of the amazing properties of a nuclear fusion reaction is that however huge the amount of energy needed to start it in the first place, the weight of a whole star, it then releases even more energy. The reason for this may seem surprising, but since you see it happening right in front of your eyes, you have no choice but to accept it. When 2 atomic cores fuse into a larger one, some of their mass disappears. The fused core has less mass than the 2 that created it. It is as if mixing 1 kilogram of vanilla ice cream with another kilogram of the same ice cream did not give 2 kilograms of ice cream, but less. In everyday life, that wouldn't happen. In the nuclear world, however, it happens all the time. Rather fortunately for us, the mass is not lost, though. It is turned into energy, and Einstein's famous E=mc gives the exchange rate. In our daily lives, we are more used to exchange rates relating one currency to another rather than mass to energy. So, to see if E=mc is a good deal for nature, imagine the same exchange rate is being offered at JFK Airport to change pounds sterling into US dollars. The exchange rate is then c, where c stands for the speed of light, and c is the speed of light multiplied by itself. For 1 pound, you'd get $90 million billion. A pretty good deal, I'd say. In fact, it is the best exchange rate in nature. Obviously, the missing mass in each single nuclear fusion reaction is rather small. But there are so many atoms fused every second within the sun's heart that the energy released is enormous, and it has to go somewhere. So it pushes out into space, away from the star's core, in as many ways as is possible. In the end, the energy from this nuclear fusion balances the gravity that presses everything down into the core, making our star's size stable. Without it, were gravity the only player, the sun would shrink. Nuclear fusion emits a tremendous amount of light and particles, which happen to turn everything nearby into a shining soup of nuclei and electrons that is called plasma. This outburst of light and heat and energy is what makes stars shine. The sun, being a star, is not a big ball of fire. Fire needs oxygen, and although the sun creates bits of it along with other heavy elements, there's not enough free oxygen in outer space to sustain any fire whatsoever. A struck match would never catch fire in space. The sun, like all the stars in the sky, is simply a bright ball of shining plasma, a hot mixture of electrons, of atoms stripped of some of their electrons, and of atoms stripped naked of all their electrons, the bare atomic nuclei. As long as there are enough tiny nuclei to press together within its core, the sun's gravity and fusion energy will remain in equilibrium, and we are lucky enough to be living near to a star that is in such a state. Actually, it has nothing to do with luck. Were our sun not in that state, we would not be here. And as you now know, the sun won't be in that state of equilibrium forever. Our star's core will someday run dry of its atomic fuel. That day, there won't be any more outward push radiating from the core to compete with gravity. Gravity will then take over and trigger the final sequence of our star's life. The sun will shrink and get denser until a nuclear fusion reaction is triggered again, but away from the core, closer to the surface. This reborn fusion reaction will not balance gravity, but overpower it, and the surface of the sun will be pushed away, making our star grow. You saw it happening during your trip into the future. A final burst of energy will then herald the death you've already witnessed, spreading into space all the atoms the sun has forged throughout its life while creating some more, the heaviest ones of all, such as gold. Eventually, these atoms will mingle with the remains of other nearby dying stars to form huge clouds of stardust that will, perhaps, seed other worlds in the far future. It is by estimating the amount of hydrogen left in our star's core that scientists can guess when this explosion will happen, and the result says that the sun will blow up in about 5 billion years from now, on a Thursday, give or take 3 days. For our cosmic family. What you've discovered about the sun so far makes you more familiar with it than any human who lived before the middle of the 20th century. All the light that showers your body day after day comes from atoms being forged in the heart of our star, from parts of their mass being transformed into energy. The Earth, however, is not the only celestial object that profits from the sun's energy. In the blink of an eye, your mind is back on the sun's bubbling hot surface and you look around, like a hawk. 8 bright dots are moving against a seemingly fixed background of distant stars. These dots are planets, matter-filled spheres too small to ever dream of one day becoming a star. 4 of them, the 4 closest to the sun, look like tiny rocky worlds. The furthest 4 are mostly made out of gas. They are still tiny with respect to the sun, but they are giants compared to the Earth, the biggest of the 4 small rocky worlds. Apart from the Earth, however, and even though they were all born out of the same cloud of dust from long-dead stars, none of these worlds and none of their hundreds of moons are a potential shelter for humanity's future. They all are bound by the sun's gravity, and they will all be gone with our star's ultimate boom. Shelter, if any is to be found, must lie further still. With a feeling of urgency, your mind shoots as far away as is possible to have a look at what lies beyond the sun's sphere of influence. Along the way, you will pay a visit to our planet's distant cousins, the giants of our cosmic family. You are about 3 times further away from the sun than the Earth is. Mercury, Venus, Earth and Mars, the 4 small rocky worlds closest to the sun, are already behind you. From there, our star is a shining dot half the size of a penny held at arm's length. A typical July midday in the United Kingdom, the hottest day of the year, say, would feel colder than the coldest winter in Antarctica, were the Earth to be here. Sunlight gets scarcer and scarcer as you move away from our star. You shoot past some rocks, leftovers from the early days of our planet's formation. They are mostly potato-shaped asteroids that, together, form what astronomers have come to call the Asteroid Belt, a huge ring of rocks that encircles the Sun, separating the 4 small terrestrial planets from a world of giants. The rocks themselves are pretty scattered and, as you fly through the belt, you realize there's hardly any chance of your hitting one of them. Many human-made satellites have flown through unhindered. Leaving the belt behind, you now fly past Jupiter, Saturn, Uranus, and Neptune, the gas giants, all enormous planets with relatively tiny rocky cores deeply hidden beneath huge, tumultuous atmospheres. All these planets seem to be blessed with a magnificent ring system, although Saturn's by far surpasses, in size and beauty, all the others combined. You fly by them all and watch them with the respect such gigantic worlds deserve, even though they are not suited for life. Beyond Neptune, the furthest planet orbiting the Sun, you may have expected to see nothing, but that is not the case at all. Another belt lies there, made of all sorts and sizes of dirty snowballs, again likely byproducts of our solar system's birth, when its current members aggregated from the leftover dust of long-gone exploded stars. This belt is called the Kuiper Belt. The Sun looks like a pinhead from out there, just another star. Hardly any warmth seems to reach these distant parts, but there is some action. Every now and then, due to collisions or other perturbations, one or more of these dirty snowballs is expelled from its quiet and distant orbit around the Sun. Pushed towards our star, it slowly reaches warmer climes and begins to melt as it speeds against the solar radiation, leaving long tails of small icy rocks shining in the dark. It becomes one of those celestial wonders we call comets. The European Space Agency's Sturdy Philae probe landed on one in November 2014 to study its surface. The Rosetta spacecraft that took it there, on the other hand, is currently following it as it approaches the Sun to watch its outermost layers turn into gas. Poor Pluto, which recently got stripped of its planet title to be reclassified as a dwarf planet, is part of that icy belt too, together with 2 other dwarves, called Haumea and Makemake. It is funny to think that Pluto, with its moon Charon, is so far away from the Sun and has so much space to travel to complete a single revolution of it, that less than one of its own years has passed between the moment it was discovered and called a planet and the moment it got stripped of that title, 76 Earth years later. It indeed took astronomers decades to see that it was actually just a quarter of the size of our own moon. The dirty brown Pluto that you now fly by of course hasn't been affected in the slightest by its renaming, and you soon leave it behind too, heading further away still from the safe protection of our shining star. Yet more dwarves cross your path, and more comets, and you even see frozen worlds that no living person has yet discovered, but your attention quickly turns entirely to a gigantic sphere that encompasses everything you've seen so far. All the planets, dwarf planets, asteroids and comets you've seen lie more or less on a flattened disk at whose center shines the Sun. But what you are seeing now does not. A reservoir of billions of potential comets forms a huge spherical cloud that seems to occupy all the space there is between the Sun and the realm of other stars. This reservoir is called the Oort cloud. Its size is astounding. It marks the boundary of our star's realm, which contains all the members of our cosmic family, a family called the Solar System. Beyond, you enter uncharted territories and head for what you reckon is the star closest to ours. It was discovered in 1915. A century ago. Just when our universe began to be understood. Its name is Proxima Centauri. 5 beyond the Sun. Your body is still on a beach somewhere on our planet, but your mind is now as far from the Earth as the furthest man-made object has ever been. As you crossed the edge of the Oort cloud, you exited the solar system and entered the realm of another star. As you crossed that fuzzy line, Asif, for you to truly understand what the boundary meant, you saw some of the solar system's outermost comets switch orbit. From a faraway curve centered on the Sun, their trajectory became a faraway curve centered on another star, the star you are now heading for, Proxima Centauri. Proxima Centauri belongs to a family of stars called red dwarfs. It is much smaller than the Sun and has a rather red hue. hence the name. Red dwarfs are very common, indeed scientists believe they account for most of the stars in the sky. As you get closer and closer to it, you continuously see it undergo violent changes in its brightness and expel huge amounts of burning hot matter in a rather erratic way. Now, are there any planets around that angry red dwarf? You don't see any. Which is a shame, in a way, for although it would be very hard to live comfortably on a planet orbiting Proxima, a civilization rising here would be able to plan for a very, very long future. When our star, the Sun, blows up, Proxima won't have changed a bit. As far as we know, it will still be shining the way it shines now for about 300 times the present age of the universe. A long time by any standards. Being smaller than the Sun, the tiny atomic cores that make up Proxima are fused into bigger cores at a much, much slower pace. Size, star-wise, does matter. The bigger the star, the shorter its lifespan. And for the planets that orbit them, distance is the key. To have liquid water on its surface, a planet needs to be not too cold and not too hot. For that, it has to be neither too close nor too far from the star it orbits. The zone around a star that allows for liquid water to remain on the surface of a planet there is called the Goldilocks zone. So what if you could find another red dwarf, with an Earth-like planet orbiting it at just the right distance? Then it could resemble our gentle world, and basically last forever. Feeling somewhat guilty for having had such a thought, you turn around to look at your home solar system, at your home world, expecting the Sun to outshine all the other bright dots in the sky, but that is not the case at all, and the sheer size of cosmic distances suddenly hits you. Were you not pure mind but instead a real space traveler, how long, you wonder, would it take to send a signal home from here? Were you to be equipped with an interstellar mobile phone, you could have tried to call some friends of yours at each of your stops, to share your discoveries with them. Mobile phones transform your voice into a signal that travels at the speed of light, making communication on Earth seem instantaneous. In outer space, however, distances are usually too large, and nothing seems instantaneous anymore. From the Moon, light takes about 1 second to reach the Earth. And another to return. Had you asked a friend on Earth if he could see you when you were up there, with binoculars, his answer would have reached you 2 seconds later. From the Sun, it would have been worse. Light takes about 8 minutes and 20 seconds to travel the distance between the Earth and the Sun. Conversations start to become tricky, since one must wait more than 16 minutes between a question and an answer. But the Sun is still only next door in cosmic terms. A call dialed now, from where you are, near Proxima Centauri, would send a signal that would make a phone ring on Earth in about 4 years and 2 months. Any reply to a query of yours would take no less than 8 years and 4 months to reach you. You have still only got to the star second closest to the Earth after the Sun, but it feels a very long way from home, so you look for something to help locate yourself, so as not to get lost. Remembering the beautiful Milky Way you saw from your tropical island beach, you look around to see where its cloudy white patch of light now lies. To your great surprise, you immediately see that it does not appear as a thick straight line anymore but like a tilted ring, with some parts brighter than others, and you somewhere inside it. You realize that if it looked like a streak from the Earth, it was because the Earth itself, under your feet, was hiding most of it. Without a second thought, having found no planet around Proxima Centauri, you head straight for the brightest part of the Milky Way. You do not know it yet, but you are now traveling towards the center of a gathering of about 300 billion stars. A gathering that has been called a galaxy. 6. A cosmic monster. When you think about it, there has to be something peculiar at the center of a gathering 300 billion stars strong. Take the Earth. Its center is the densest, hottest, harshest place there is. Take the solar system. At its center lies the Sun, the densest, hottest, harshest place there is. This may not prove anything, but it hints that there is probably something big happening at the center of a galaxy too. Something really big. As fast as thought, you fly by tens of millions of stars. Some are much bigger than the sun, doomed to live even shorter lives, and others are tiny, ready to shine their light for time beyond imagination. You also fly through stellar nurseries, dust clouds made out of the remains of hundreds of exploded stars, and stellar graveyards waiting to merge and become stellar nurseries. And now there you are. Near the galactic center, whatever that means, and you suddenly stop. Right in front of you, there is a ring again. A spinning, colorful ring made of scattered matter. Looking more closely, you see it is made of gas in billions of rocks and comets all moving around a thick, donut-shaped source of bright, energetic light. What is happening here? What are these rocks and icy fragments that are moving around? You look around a little further, and what you see seems not to be possible. It is not only lost boulders that orbit that ring, there are stars too. Whole stars. Not planets. Stars themselves. And they are moving fast. As of 2015, one of them is actually the fastest known object in the universe. It is called S2, or Source 2. From the Earth, scientists have seen it complete an orbit around the donut in about 15.5 years. Given the distances involved, that means it moves at an astonishing 17.7 million kilometers per hour. But how can that be? What beast has enough gravitational power to keep such a lightning-fast object close by? Is it even possible to generate such a force? Imagine a marble and a salad bowl. If you spin the marble too slowly against the wall of the salad bowl, it will immediately fall down to the bottom. If you spin it too fast, it will spiral up and fly out to break something in your kitchen. But if you spin it right, it will move around for a moment, in a circle, some distance between the bottom and the top, without escaping the bowl, without falling, until friction turns too much of its velocity into heat and slows it down. Now, imagine that the marble is this superfast S2 star and that there is an invisible bowl keeping it in orbit around whatever lies within the bright donut. In space, there is no friction, so there is no reason for the star to lose any of its energy. From the speed of S2, we can thus imagine the shape of the bowl and hence what mass lies at the bottom. This rather straightforward calculation has been made many times by scientists, and it always gives an incredible answer: to create a gravitational field with the right strength for S2 not to be hurled away into outer space, the mass of more than 4 million suns is needed. That would be a huge star indeed. But we have a problem: there is no visible star within the orbit of S2. You can look for one as much as you like, you won't find one. From Earth, to see what this 4-million solar mass object that keeps S2 from flying away is, scientists have built telescopes able to detect specific light that our eyes cannot see, namely either ultraviolet light or, for a more impressive vista, the second most energetic of all the lights we know, X-rays. Using such a telescope, they still cannot see an object, but they do see energetic bursts of light originating within the ring, from some tiny location there. What keeps S2 from shooting away not only isn't a star, it is also far from being as big as it should be. So much so, in fact, that scientists have only one explanation for what must be hiding there: a black hole. A supermassive one. Scientists have called it Sagittarius A, but they can't really study it clearly from the Earth, its surroundings being hidden by all the stars and dust and gas that lie between its location and our planet. You, however, are right next to it, and if you wonder what triggers these bursts of energetic light that telescopes on Earth detect, you are about to find out. Understandably, though, being right next to an invisible monster, you don't feel very secure. Who knows what a black hole could do? Could your mind get swallowed, possibly never to be reunited with your body? Could it get stuck in there and doomed to wander away from everything you know? Or could there be a hidden passage, a door leading to another universe, to another reality, as you may sometimes have heard people say? Uncertain what to do, you stare at the billions of tiny particles of dust and other small rocks that make up the bright ring. Less than a minute later, a huge potato-shaped asteroid flies past you at 1 million kilometers per hour. You watch it carefully. As it speeds through the ring, you see it melt into tiny specks of molten matter, burnt by the friction caused by the ring's dust. Just as a small rock entering the Earth's atmosphere might become a shooting star and burn up entirely without making it to our planet's surface, the asteroid disappears long before it could reach whatever lies inside the donut. As you turn around again to look for more action, it is not just a big piece of rock that you now see coming your way. It is a star. A big, shining, furious star. Like S2. But bigger still. Will it burn too? Will it get through? You see it dip towards its fate and fly through the donut at an angle. It is now within the ring and out of sight, but it promptly reappears, after completing half an orbit, in a strangely distorted way, as if a mirage caused by some weird force caused it to change shape. It continues to fly down. Tremendous stresses seem to be acting on it. Planet-sized chunks of the star are snatched off its surface. You try to stay calm, praying that there is nothing to fear, but you can't help it, and your thoughts suddenly feel weary and heavy, preparing for a disaster of mind-bending proportions. Until now, you were ethereal, oblivious to whatever forces were ruling the universe, but that is not the case anymore. Loaded with heavy thoughts, you become subjected to gravity and you are in the presence of its master. Against your will, you are dragged inwards, you are being sucked in, as if sliding on an invisible yet slippery slope. You cross the ring of heated matter and get close to the infalling star, now ripped apart, as it bursts into a blazing wing of white-hot plasma that spirals downwards, taking you in, towards the still invisible black hole. Needless to say, your fears are all justified. Hundreds of billions of tons of plasma are plunging in with you. Your heart beats like mad as you spiral down faster and faster. And faster until a tremendous whirlwind force ejects you out. What remains of the star is transformed into extraordinarily powerful jets made of what seems to be matter turned into pure energy. Confused, you wonder if you've just slid into a parallel world inside a black hole, but you soon realize that you didn't, that you are moving away from the monster, that you've been ejected, or rejected, by the master of mass. The Milky Way's giant ring is now apparent again, far away. Like that marble made to spin too fast against the wall of a salad bowl, you and the dust from the disintegrated star have been expelled before having reached whatever the black hole is made of. You fell in too fast and got slingshot away before reaching the invisible monster, and so did the star, whose matter turned into two jets of the most energetic types of light known to mankind, X-rays and gamma rays. One is shooting up and the other down, like two beacons aiming their lights not just to the gaping space between the stars of the Milky Way, but further still, towards greater voids. The jet's speed is astounding, and so is yours. You are being carried away and fly by millions of stars, as if a giant finger wearing the Milky Way as a ring was pointing to your destination. Maybe it wasn't yet time for you to take the plunge into a black hole. Maybe nature wanted you to see more of our universe's beauties before allowing you to travel within a black hole's deadly grip. Whatever the reason, your heart recovers and your thoughts become light again, ridding your mind of gravity's grasp. You are far away and have recovered the freedom to move as you please. Still, you follow the jet for a moment to see where it leads. And it doesn't take you long to see that something strange is happening. The surrounding stars seem to be less and less numerous. So much so that soon there aren't any ahead of you anymore. Some sources of light are still shining far away in the distance, but they really are much further than anything you've seen so far. Strangely, also, the Milky Way ring is gone. Wondering where it went, you look down and gasp at the most extraordinary vista you've ever seen. No human being or man-made object has ever been blessed with such a sight. Earth-based observations have sneaked a few images of the surrounding of the black hole you've just escaped, but not of this. Were you to call Earth from your present position, a reply, if any, would take more than 90,000 years to reach you. You are above the Milky Way. Your galaxy. If you thought, looking up at the night sky from your sandy beach, that it must spread all the way to the end of the universe, you now see that it doesn't. Far from being everything, the Milky Way is but an island of stars lost in a dark immensity of a far larger scale. 7. The Milky Way. The first men to have been to space all came back humbled by the beauty of our planet and by its tiny size in an ocean of blackness. But that was just the beginning. What you are staring at now is more humbling still. You knew the Milky Way was a galaxy, but only now do you see what that really means. From above, the whitish cloud in the Earth's night sky doesn't look like a cloud at all, but like a thick disk made of gas and dust and stars. Right underneath you, spreading over distances so large that light would take tens of thousands of years to cross, 300 billion stars, bound together by gravity, are spinning around a bright center. If you think of the solar system, with its planets and asteroids and comets, as our cosmic family, if you think of Proxima Centauri as our neighboring star, then the Milky Way can be thought of as our cosmic megalopolis, a thriving city 300 billion stars strong, the Sun being just one of them. Intertwined within a whirling dance, surrounded by emptiness, it is such gatherings of stars and dust and gas that scientists call galaxies. And just as our star has been named the Sun, the Milky Way is the name we have given this particular galaxy, our galaxy. For huge bright spiral arms separated by dark patches swirl around its center, where they meet up in an even brighter bulge of gas and dust and stars that hides everything down to the black hole you've just escaped. Only the jet of energetic matter being expelled from it, the jet you've traveled with, is visible from where you are. If you have a hard time grasping what 300 billion stars floating on their own actually means, do not worry too much about it, nobody really can. But if you were to try to explain what you are seeing from up there to your friends once back on your tropical island, numbers won't help. Instead, tell them to pick a cubic cardboard box 1 meter high and fill it to the top with coarse sand from your beach. Now ask them to fill 300 such boxes with the same sand. There are as many stars in our galaxy as there are grains of sand in all these boxes taken together. Kindly ask your friends to fly back to London and pour the contents of these 300 boxes in a disc shape covering Trafalgar Square, and to draw 4 spiral arms on it. Then tell them to sit on Nelson's shoulders. That's what the 300 billion stars of the Milky Way look like to you now. And if you tell your friends that you marked one of the grains of sand with a yellow dot before they winched themselves up, ask them to figure out which one it is. They'll realize how hard a time your mind is having up there, above the real Milky Way, figuring out where the Sun is. Not to mention the Earth, which is 100 times smaller. Finding a star is hard, but planet hunters have a harder job still. From above the Milky Way, to find the Sun, your mind does however have an advantage over your friends. You can imagine all the night sky pictures that have ever been taken by humans, from Earth and from space alike, to compare them with what you now see. Over the years, scientists have created a map of our galaxy's stars, and without ever leaving the Milky Way, they have a fairly precise idea of where the Sun lies within it. To match the pictures of the night sky, you first concentrate your efforts near the galactic center, near the bulge and the black hole, where all is bright and beautiful and powerful. Wouldn't it be natural for a species as important as ours to have blossomed in, or quite near, that very special position? Wouldn't it be logical, given our importance, and so very right, for the Sun and the Earth to be part of that galactic magnificence? Well, they are not. The solar system lies about 2/3 of the way between the central black hole and the outskirts of our galaxy, somewhere on one of the 4 bright arms. Not a special place whatsoever. And to further rub salt in the wound, as you shall now witness, however huge it may be compared to us, even our galaxy itself is pretty insignificant on the cosmic scale. Turning around to face whatever is left out there to see beyond the Milky Way, you catch sight of some shining blobs that seem to light up the far distant universe. You wonder, Are they loose stars, these blobs? They seem a bit too smeared out. And far away. Are they? Could they be galaxies too? Can you see them from the Earth with the naked eye? The answer to the latter question is no. On Earth, every time you've raised your eyes towards the night sky, all the stars you have ever glimpsed a twinkle of belongs to the Milky Way galaxy, to the spiral disk you've just seen. All of them. Even those stars that seem rather far away from the whitish band that streaks the night skies. The Milky Way is not an infinite sphere but a finite disk, and the Earth happens not to be at its center, but rather closer to its edge. Different directions in the sky hence look very differently filled with stars, just as the night sky is different seen from different places on Earth. Each place faces a different part of the Milky Way. It so happens that the Earth's axis is tilted in such a way that the southern hemisphere always faces the galactic center while the northern hemisphere always looks away from it, where there are far fewer stars. Accordingly, nights in the north are rather dull compared to southern ones. From your tropical island beach, what you called the Milky Way was just a slice of your galaxy, a band containing hundreds of millions of stars too far away to be seen individually, but whose lights, together, formed the cloudy band. As you now peer into the faraway unknown, ready to make your mind bounce towards whichever place you find most mysterious, you suddenly realize that all these blobs of light look as fuzzy as the Milky Way. They must be galaxies too. And as you think so, right there, at an angle, another galaxy suddenly rises. The sight is astounding. Its edge appears from underneath the Milky Way and it is now growing fast. It is Andromeda, our local galactic big brother. It is so big that it is hardly believable that it took so long for mankind to discover what it was. From Earth, Andromeda spans a part of the night sky that is about 6 times as large as a full moon, but it is so far away that despite its 1,000 billion stars, only its central bulge can be spotted with the naked eye. And that bulge is tiny. The first human to notice it was the extraordinary Persian astronomer Abd al-Rahman al-Sufi. Around the end of the first millennium, more than 1,000 years ago, when many, throughout the world, spent their short lives fighting each other, inventing cunning torture devices and fearing the end of the world, he watched the stars. Al-Sufi was one of the greatest astronomers of the Golden Age of Baghdad, but, describing Andromeda's central bulge as a faint cloud of light, he had no way of knowing that it was another galaxy. He did not even know what a galaxy was. Actually, that knowledge came about 1,000 years later. No one knew about galaxies as separate gatherings of stars until the 1920s and the observational works of Estonian astronomer Ernst Öpik and U.S. astronomer Edwin Hubble. They were the first to notice that there were great expanses separating these other groups of stars from the Milky Way, making them separate entities in their own right. Andromeda is the closest cosmic proof that the Milky Way is not the entire universe. As you look at it, as you realize that the Milky Way and this majestic spiral of 1,000 billion stars whirl around each other, you also become aware that all the galaxies in the universe are engaged in a cosmic ballet, a ballet where the dancers are lone shining islands, gatherings of billions of stars moving within the dark emptiness of space. Spanning the cosmic horizon, an extraordinarily powerful feeling crosses your mind as it starts to encompass the Milky Way, and Andromeda, and other galaxies both near and far. In a pure, blessed moment, you suddenly see everything. Tens, hundreds, thousands, millions, hundreds of millions of galaxies. Everywhere, forming groups of various sizes. Forming weird, filament-like structures that crisscross the whole visible universe. Who would have thought? A few minutes ago, or is it hours? You were lying on a beach, on holiday, and now the entire visible universe is contained within your mind. You've reached such a viewpoint that the dots studding the universe are not lone stars anymore, but groups of galaxies, each group containing thousands of galaxies, themselves made out of hundreds or thousands of millions of stars, the Milky Way being but one of them. As you embrace this amazing picture, as you look at all these places, you can't help thinking that you'd have the same trouble finding your home galaxy out of all the others as you'd have finding the sun within the Milky Way, or a grain of sand in Trafalgar Square. Still, you set your mind free and shoot at the speed of thought and see galaxies spin and dance and whirl, and get torn apart and smash against one another, and you witness tiny ones disappear as they purely and simply are swallowed by some giant neighbor. Now wait. Should you worry about that? In a blink, you are back near the Milky Way. Andromeda is overhead. It is huge. Could it be that it, too, will one day merge with the Milky Way? The two galaxies are certainly moving around each other, but something else is going on. Sharpening your gaze, you suddenly jump as you realize that Andromeda and the Milky Way really are falling upon each other at the astonishing rate of 100 kilometers per second, leaving just 4 billion years before they collide. They will start to merge 1 billion years before the sun explodes. Gulping painfully, wondering how humanity could ever be saved from that, a note of relief crosses your mind. Galaxies are so big, and there is so much space in between any stars within, that galactic collisions hardly ever make stars smash into one another. There is a risk, sure, but you'll have to live with it for now. It is absolutely normal, at this stage, to go through a Copernican philosophical depression. You may even begin to wish you were still living a few millennia ago, when the Earth was flat and, for the obvious reason that we humans like to consider ourselves special, at the center of the universe. How reassuring it must have been to believe that everything revolved around us, that angels were spinning some sacred wheels attached to a cosmic clockwork mechanism, making the stars and the sun move. Why on earth did the 15th century Polish mathematician and astronomer Copernicus have to ruin all this and proclaim that the sun was not orbiting the Earth? Why did the 17th century mathematician and astronomer Galileo see that Jupiter had moons that were not orbiting the Earth? Why did Opie and Hubble see that there were other galaxies out there? Why? They started all this. Well, besides the fact that they were right, without the likes of Copernicus and Galileo and so many others, humanity would be doomed and, which is arguably worse, I would never have written this book. You would never have traveled by thought alone through our cosmic vicinity, not to mention beyond. And between you and me, wouldn't it be a shame if all the beauty that is hidden out there were left unseen, or unexplored, or worse still, left only for other intelligent species to see from their own faraway cosmic perspective? And again, while we're on the subject, and as the sheer size of the visible universe starts to sink into your mind. Do other species actually exist? Within those billions upon billions of star groups that stud an otherwise dark universe, are there red dwarfs like Proxima Centauri circled by planets of their own? Are there double sun systems shining upon inhabited worlds? Are there other Earths? It may seem scarcely possible to believe we're alone in this gigantic universe. If it's just us, seems like an awful waste of space, wrote U.S. astronomer and cosmologist Carl Sagan in 1985, and yet, 30 years later, no one from Earth knows. The existence of alien life is still an exciting possibility, but for now it's just that, a possibility. This may change very soon, however, as our telescopes start discovering more and more worlds out there. I, for one, very much hope so anyway. Even during some of the darkest years of humanity's chaotic past, some people heroically defied the religious authorities by asserting that, indeed, other worlds probably existed. The Italian Catholic monk Giordano Bruno, for one, got burnt alive in Rome in 1600 for having dared to speak such a heretical thought out loud. He had claimed that there were countless suns and countless Earths all orbiting around their suns. He died in agony for believing so. Today, even if, in my opinion, far too many people would rather play deaf and blind than face some facts unraveled by science, we know better than any inquisition. Potential Earth-like planets have been found, and the likes of Giordano Bruno have been vindicated many times over, albeit rather recently. Humanity has known about the existence of planets like Jupiter or Venus for ages, that is true. But the first time in history someone actually saw a planet orbiting a star that is not the Sun was only 20 years ago, when, in 1995, two Swiss astronomers, Michel Mayor and Didier Queloz, spotted a giant world, which they called 51 Pegasi b, orbiting a star located about 60 light-years away from us. The planet Mayor and Queloz found is not habitable, though, if only because it is far too close to its star. Still, it is a planet. Following their discovery, a few other such worlds were found each month, until specially devised satellites were sent to find more. NASA's Kepler telescope, launched in 2009, is one of them. Today, more than 6,000 candidate worlds have been detected. Out of these, about 2,000 have been confirmed as being planets orbiting faraway stars. Some are even double star systems, and many other surprises are sure to break future news. To differentiate them from Venus or Jupiter and the other planets that are part of our Sun's family, these faraway worlds are all called exoplanets. And by the way, out of the 2,000 confirmed exoplanets, about a dozen are potentially Earth-like, and one of them, whose existence was confirmed in 2014, does bear stunning similarities with our Earth. All of these other worlds may be barren, of course, but they may also harbor life. In fact, I am ready to bet that direct or indirect signs of extraterrestrial life will be found within the next 2 decades or so. Maybe on one of these candidates, or on some yet-to-be-discovered ones. The technology is almost there for us to detect signs of biological activity within the atmosphere of such remote worlds. It would be great to live through such a discovery, wouldn't it? Now, all the exoplanets that have been detected so far are within the Milky Way, our galaxy, and thus rather near to Earth. Planets that could exist in other galaxies are much too far away for any of our telescopes to spot, even though there may be hundreds of billions of them out there. Andromeda, for one, may very well be teeming with life. It is the largest of all the galaxies that surround ours. And it is very close. On a galactic scale, that is. Not on a human one. A call made right now from Earth to some place around one of its 1,000 billion stars would take about 2.5 million years to reach its destination. If we were to make contact, we'd better find an intelligent question to ask. And an appropriate language too. 8. The first wall at the end of the universe. Now, how big is the visible universe? What would happen if you were to shoot straight out into what can be seen, for as long as is possible? Is there a limit to it all? Well, since someone is, sooner or later, bound to ask you that once you are reunited with your body, you'd better try to figure it out. With confidence, you pick a random direction and head for it. As you start moving away from your home galaxy, you immediately realize that the Milky Way is part of a little group made of 54 galaxies gravitationally bound to each other. Scientists have called that group the local group. It spans a sphere about 8.4 million light-years wide. The Milky Way is its second largest member, Andromeda being the king. Beyond lie other groups of galaxies. Some of them are several hundred galaxies strong. These big gatherings, much larger than ours, are called clusters of galaxies. As you keep shooting ahead, you fly by giant clusters, superclusters, containing tens of thousands of shining spirals and oval disks made of countless stars, all bound to each other by gravity and stretched throughout space and time. These superclusters form mind-bogglingly large structures. As you shoot away from everything you know and look at the universe on a different scale, you realize that you will once again have to reconsider your relative size in the grand scheme of things. Your mind's eye wide open, you turn around, and you look everywhere, gathering as much light as is possible from all possible directions, searching for an end to all this. There is no notion of up or down, no difference between left and right. You are now more than 1,000 million light-years away from the Earth, and billions upon billions of shining galaxies are spread throughout an unbelievably large darkness. Around you, near and far, galaxies and groups of galaxies and clusters and superclusters are separated by distances larger still, larger even than all the distance you've traveled so far. That the Milky Way is but one of all these dots is barely believable, and yet you know that what you see is no fantasy, but what is known to mankind. Still, true facts or not, the idea of saving the Earth no longer seems to make any sense at all. Why bother? Why care? Understandably, leaving everything behind and letting yourself forever drift in this beyond beautiful hugeness of a reality even becomes an appealing dream. Why not spend your life up there? Is that what scientists do, daydreaming in their laboratories? As you contemplate the idea of never returning to your daily life, a strange feeling catches you and begins to inject a new energy back into your mind. Somehow, all you are now seeing, all you are now moving through, is what mankind understands the universe to be. Somehow, you are traveling through the universe as it is pictured by human minds, so all this immensity has to be contained within the limits, if there are any, of a human brain. As amazing as it may sound, it is a reassuring idea, and it brings you back to being a human being, a member of a species able to project its thoughts as far as the eye can see, and far, far beyond. Embracing the space's cape, you wonder, could the magnitude get still bigger than this? Could your mind embrace even more? Whatever the fate of the Earth, you decide that you'd rather know than not. Your virtual heart thumping with renewed curiosity, you desperately head forward and fly past thousands of millions more galaxies. As is invariably the case with humans, familiarity soon sets in, and even the universe's immensity ceases to shock you. What may have felt like desperation a second ago now seems to have turned into joy. Here and there, you see galaxies colliding, you see stars burst into superstars, supernovae, outshining billions of their siblings for but the wink of an eye. Throughout the universe, everything moves around everything, you are being blessed by a show of amazing proportions and inhuman beauties. Heading forward without looking back, you are now 10 billion light-years away from Earth. Your mind keeps flying ahead and away. You are 11 billion light-years from the Earth. 12. 13 billion light-years away, and counting. And you now feel elated, and you look for the end of our universe, and you see none, but your mind slows down slightly, for the galaxies around are getting scarcer. And the stars they are made of seem to be getting bigger. Enormously so, in fact. Some of the stars you now see are hundreds of times bigger than the average stars of today's Milky Way. You keep moving forward, albeit at a slower pace. The number of shining sources of light in front of you has now fallen drastically. And as you reach a distance of about 13,500 million light-years away from Earth, pretty much all sources of light are gone. You stop. Could you possibly have reached what you were looking for? Does the universe actually have an end? You remember having raised the question a couple of times with your friends prior to your tropical island trip together, but you had never given the thought a real meaning. And now you wonder, did you think you could eternally zoom out from Earth into the outer universe and continue to see galaxies? Well, since you are traveling through the universe as it is seen from Earth, let me say this, our telescopes have shown us different. There is indeed a limit to what we can see, and will ever be able to see, using light. Your mind hasn't reached that limit yet, but it soon will. For now, it is traveling through a place so remote in space and time that the first stars weren't even born. For this reason, the place and epoch you are crossing has been dubbed the Cosmic Dark Ages. Any light we see coming from there has traveled throughout the universe for 13.5 billion years to reach us. It is back then, in a stretch of time lasting about 800 million years, that the first stars began their job of transforming small hydrogen and helium atoms into the matter we, and other planets and stars, are made of. These were the first generation of stars, our Sun being a second or third generation one. As you continue to fly forward, expecting the darkness to prevail forever, you suddenly reach a place through which light cannot travel anymore. The surface of what seems to be a wall in space and time. Beyond, the universe is not dark. It is opaque. You stop right in front of it and cast a virtual hand forward to gently probe what lies beyond. Goosebumps spread over your non-existing flesh as you touch what seems to be a tremendous amount of energy. An energy so dense that you suddenly understand why light cannot travel there. It would be rather like lighting a torch within a wall. Light exists beyond the surface you are facing, but it has no freedom to travel at all. What you have reached is not a product of your imagination. It is the furthest place our telescopes can see. It is the place in space and time where and when our universe became transparent. No light from beyond, no light from before that time, will ever reach the Earth in a straight line. No light from before that place will ever be caught by any of our telescopes. It took many decades for theoretical physicists to understand what this meant. In the end, as you shall see in the next chapter, they came up with a rather bright idea to make sense of it all, and this idea is called the Big Bang Theory. For now, however, you'll have to accept that you just reached the end of the visible universe. It is a surface that has been detected and mapped with our telescopes. The surface of a wall that no light can cross. It has been called the surface of last scattering. But just as you start realizing how weird and unexpected all this sounds, everything disappears around you and you find yourself back on your tropical island beach, looking up at the night sky. The stars are still there, and so are the trees and the sea. And so are your friends. They are looking at you in a rather peculiar way. You sit up and tell them the extraordinary journey you've just been on. The sun dying, we need to find a solution to that problem, the universe so big it's crazy. And the wall! Out there, the wall that marks the passage from opacity to the dark ages. Your friends' peculiar looks turn into worried ones. As they help you up and walk you back to your villa, you can hear them wonder if perhaps the barbecued shrimps were not fresh, or the alcohol too strong. Come on, guys, you try to insist. I can't have made that all up, you know that, right? To the east, a few hours later, some of the rising sun's rays begin to bounce off the dust contained in the Earth's atmosphere, diffusing all around, hiding space away from view. Lying down on your bed, surrounded by early morning birdsong, you open your eyes and see the silhouette of one of your friends standing right next to you. She apparently kept watch over you throughout the night. Did you dream it all? You wonder. Did your mind really travel through the vastness of space? As your friend asks you if you are feeling better, holding a glass of water out for you, a fresh morning breeze gently caresses your forehead, and you smile, thinking that either way it feels good to be back on Earth. And then you smile even more, for deep inside yourself, you know that you experienced something very special and dreamt none of it, that it was all true, that you were blessed with seeing without having to study for years. For some reason unknown to you, you saw the universe as it is known today. Relieved to see you smile, your friend stands up to fetch you some breakfast. As soon as she is gone, however, you immediately try to recall what you've been through, not to forget, with the feeling that this was only the beginning of a very strange adventure. Sitting on your bed of woven palm leaves, watching the waves wash over the seashore, you remember the Earth as seen from space, a tiny dot of blue orbiting the sun. You remember the other stars, billions of them, swirling around the central black hole that hides near the center of the Milky Way, our galaxy. Then you remember Andromeda and the 4 dozen or so galaxies that make up the local group, and then you remember the other groups in galaxy clusters and superclusters that spread far, to infinity and beyond. No. Not to infinity. To the dark ages and the wall. The surface of last scattering, beyond which no light can travel freely. And you know that whatever direction your mind might have taken on its journey, you'd have ended up hitting that wall. This pretty much sounds as if, on a scale much larger than anyone could ever imagine, the Earth was in the middle of a sphere whose boundary is made of that wall. What lies within that sphere may well be the entire visible universe that will ever be accessible to mankind. As you let that thought sink in, you blankly stare right in front of you, at the horizon. If the surface of last scattering surrounds the Earth, then the Earth has to be at the center of a sphere bounded by that wall. That sounds logical. But then, that means the Earth is at the center of its visible universe. Shocked, hardly believing it yourself, you shake your head and mutter that none of this makes sense. It makes no sense at all. Still, you know what you saw, and you suddenly wish you could get back up there and have another look at it all. Which you will, but from a different perspective, very soon. To prepare yourself, let me just say that the surface you saw, the surface of last scattering, is not the end of the story. There are at least 2 other surfaces beyond, with walls behind them. The first one is called the Big Bang itself. The second one hides what caused the Big Bang. Before you reach the end of this book, you'll travel all the way to that second wall, and beyond. But first, you should take it easy. You are on holiday, after all, and your friend is back with your breakfast. While you eat, however, I'll help you bring some order to what you've been through. Part 2. Making Sense of Outer Space. 1 Law and Order. Have you ever tried to jump off a cliff? Or through a window from the top floor of a skyscraper? Probably not. Why? You'd be dead. And so would I, if I were to try it, and so would anyone. Now, why do we all know this? The answer is as straightforward as it is mysterious and deep. In it lies the reason why the human race has already managed to conquer the Earth and a small portion of the sky. In it lies the reason why we managed to send you to look at the stars in the first part of this book. It has to do with nature and its laws. However learned we are, whether we liked science at school or not, whether we are scientists or not, if we search deep within ourselves, we all have the intuition that there are laws in nature, and that these laws cannot be broken. That anyone jumping from too far up is doomed to fall towards a splashy end is one of them. Over the millennia that separate us from our hunter-gatherer ancestors, many men and women have continuously been searching for these laws. And they managed to find some, too. Today, the field that endeavors to continue this quest and further unravel the mysteries of nature is called theoretical physics, and it is its kingdom whose doors are about to open for you to travel through. This kingdom was arguably built when English astronomer, physicist, mathematician and natural philosopher Isaac Newton created a new language, that of mathematical analysis, which allowed him to describe pretty much everything that is within the reach of human senses. Why, when a person steps from a cliff, he or she falls rather than walking on air, is given by a formula. As long as we know how the fall starts, Newton's formula tells us where and how fast the fall will end. The same formula also says that there is no difference, when falling from a cliff, between a human, a sponge or a piece of rock, as long as we forget about the drag of air-induced friction. It also says that the moon completes an orbit around the Earth in a little under 28 days, and that the Earth revolves around the Sun once a year. That particular formula is called Newton's universal law of gravitation. For this, Isaac Newton is still considered today as one of the greatest minds of all time. There is no need to be a scientist to guess that finding such a law must have felt very good, and Newton must have been very pleased with himself indeed. Strangely, however, instead of throwing parties every night to celebrate, he preferred to make sure he was right. So he started to check if his gravitation formula really deserved to be called universal. Scale is of the essence here, because as you've already figured out in the first part of this book, compared to the universe, the Earth isn't much to shout about, to say the least. And what is true for a tiny speck of dust may not be true for a galaxy. On Earth at Newton's time there was not a single experiment that could prove his formula wrong or even challenge it. An arrow, for instance, always landed where it should. And a mountain would have too, had someone thrown one. Now, what about even bigger things? What about places where gravity's effects are more intense than those found on our planet? To figure that out, we have to look beyond the Earth. And since you've already been touring the nearby universe, you know that the most obvious and easiest place to start checking is also the brightest, the Sun. A troublesome piece of rock. Our star's surface gravity, the way it pulls you down on the surface, is about 28 times stronger than our planet's, but the Sun is not the most gravitationally powerful object you encountered while discovering outer space in the previous part of this book. Black holes, for one, are much more potent. Still, the Sun outclasses the Earth. And it is much easier to probe than black holes. So, does Newton's formula work around our star as well as it does around our planet? And how could we check? As you've seen, there are 8 planets in the solar system. From the furthest from the Sun to the closest, these include Neptune, Uranus, Saturn, Jupiter, Mars, Earth, and Venus. Maybe we could have a closer look at how they shoot through space, and check whether or not the Sun pulls them towards itself the way Newton's law says it should. Thanks to many astronomers who put aside their family life to look at the stars throughout their nocturnal existence, humanity even had a precise description of some of these orbits by Newton's time. 11, and the answer is almost too good to be true, if one takes into account how the planets interact between themselves too. All the planets listed above 12 move precisely according to Newton's formula. What a relief! The formula really is universal after all. Newton's mother must have been very proud. But wait, hold on. Those of you with sharp eyes will no doubt have noticed that one planet is missing in the list above. We've only named 7 of the 8 planets that belong to the solar system. We've forgotten one. The one closest to the Sun. The one that feels the Sun's gravitational pull more than all the others. Mercury. And with Mercury, there is a tiny problem. A slight mismatch. Nothing big. Something so small that, surely, it can't matter much. But it does. Over the couple of centuries that followed Newton's work, this slight mismatch changed everything humanity knew about space and time. Mercury isn't that impressive. Only slightly larger than our moon, it is the smallest planet of the solar system. It is rocky and its surface is battered with craters that are unlikely to disappear anytime soon. Mercury has no atmosphere, no weather to smooth out irregular shapes and scars. In short, Mercury is not the kind of planet one would choose as a holiday destination. To complete a full spin on her axis takes her 59 Earth days, meaning that a night on Mercury lasts a month on Earth, and is followed by a similarly long day. Both day and night on Mercury are hellish. Daytime temperatures can reach 430 degrees Celsius only to drop at night to 180 degrees Celsius. Newton did not know these details, and he probably couldn't even guess how harsh a world Mercury is. Today, we know. And today, we also know that according to his formula, the trajectory of all the planets around the Sun should look like a slightly squashed circle. As I said above, for all the planets, Newton's calculation was in perfect agreement with observations. Were they to leave a trail behind them, each of the planets would draw a squashed circle, an ellipse, in the sky, a path they would pretty much retrace year after year, just like Newton said they should. But not Mercury. Mercury's orbit happens to spin on itself, like an egg tumbling end over end, so that Mercury does not retrace the same path twice. This is mostly due to the other planets. They pull tiny Mercury towards themselves every time they get close, as Newton had already guessed. Mostly, though. Not entirely. The mismatch is tiny, but it is there. Visualize the space between 2 consecutive seconds on a watch and divide that space by 500. A single one of those divisions is the angle by which Mercury's squashed circle drifts away from Newton's calculation over a century. It may seem unbelievable that such a tiny drift could ever be identified without scientists having to wait some hundreds of thousands of years, but it was. Worse, we now know there is no way Newton's formula could predict it, let alone explain it, because that mismatch has to do with an aspect of gravity far beyond whatever Newton could have imagined. Newton's equation quantifies how objects attract each other, but it says nothing about what gravity actually is. Poor Isaac actually spent a rather large amount of time trying to understand where gravity came from. Is it a property of matter itself that makes objects attract each other? Are all objects in the universe linked? And if so, by what? No visible or invisible elastic rope has ever been detected between our feet and the ground of our planet, or between the Earth and the Moon. And what about a magnetic link? Well, magnets do not stick to our feet when we try to hold them there, because our bodies are electrically neutral. Gravity can't be a magnetic force, then. So what is gravity? And why does stubborn Mercury, the tiniest of planets, beg to differ from the others? Newton died in 1727. He had failed to find an explanation. 188 years passed before someone suddenly came up with a rather strange new idea. 1915. The good thing about research in physics is that when observations fail to be consistent with theory, the first thing we say is that the observation must be wrong. Then we try and do the experiment again, and when experiments stubbornly and repeatedly give a wrong answer, we check if, by any chance, someone unknown had predicted such an outcome using an alternative theory. If the answer turns out to be no, it is fair to assume we have no idea whatsoever why nature behaves this way. The safest option is then to try everything out. Obviously, everything includes the craziest ideas, and that, I have to say, is a lot of fun. As we shall see later, ideas that are being probed today to figure out how our universe was born are worthy of the best science fiction models. In general, of course, most of these ideas are completely wrong. But never mind. What is important is to search and see what happens. So far, this approach has worked rather well. Newton's formula had thus been used for nearly 2 centuries without any problems, and, to be fair, Mercury's case did not have much impact on most people's lives. But then, a scientist came up with a completely deranged idea about gravity. Imagine the sun, in space, with Mercury spinning around it, and forget about everything else. They are alone in the universe. A small rocky planet orbiting a huge shiny sun. Emptiness all around. Now get rid of Mercury. And get rid of the sun too. What if gravity had something to do with that nothing that is left, i.e., with the very fabric of the universe? To figure out what could happen if this was the case, let's put the sun back and think. If we assume for a moment that the fabric of our universe can be molded, one of the simplest interactions the sun could have with it is to bend it. How might that happen? Well, try to picture a heavy ball lying on a stretched rubber sheet. The rubber will bend downwards around the ball. If you then cover the rubber sheet with soap, anything walking on it, an ant, say, that gets too close to the bent part will slip towards the ball, downwards. For the ant, that effect could be felt as gravity. Obviously, if the stars and the planets were all lying on a soapy rubber cloth, I should hope we'd have noticed by now. So the fabric of the universe can't really be a flat, solid rubber sheet. However, it might be a 3D invisible one, or even a 4D one. And whatever that voluminous fabric were made of, why not imagine it bending around the matter it contains? Not just along a plane, of course, but in all directions, as if a ball immersed in the ocean were bending the water around it. Taking this idea seriously for a moment, gravity would then merely be the result of that bending. Whenever one falls not because of a force that pulls things down, but because one slips down an invisible slope in the fabric of the universe. A crazy idea, yes, but why not, after all, give it a try? How might things move in a universe like this? For all the planets up to Mercury, geometrical calculations using this bending theory actually give the exact same results as Newton's, which is as reassuring as it is exciting. So what about Mercury? The man who came up with this deranged idea of a bending found that, in a universe like the one he described, the squashed circle of Mercury's orbit should spin around the Sun in a way that does not agree with Newton's calculation. By how much? By an angle corresponding to about 1/500th of a second on a watch. Every century. Amazing. For more than 15 decades after Newton's death, nobody was able to figure that out. But he had. He was right. Gravity suddenly wasn't a mystery anymore. Gravity was a bending of the fabric of the universe caused by the objects it contains. Newton had not seen this. No one had seen this before, and we are still trying to figure out all the consequences of this vision today. Stephen Hawking has often said, "I wouldn't compare the joy of discovery to sex, but it lasts longer." A single look at the picture of the man who solved Mercury's problem seems to confirm that statement. His name is Albert Einstein, and the theory we've just introduced, the theory that links matter and the local geometry of the universe into a theory of gravity, is called the general theory of relativity. This theory was first published in 1915, a century ago, and scientists took some time to realize that Einstein had incidentally revolutionized our vision of everything. Contrary to what everyone had believed before him, he had found that our universe not only could have a shape, but that it was dynamic, i.e. able to change with time. As stars and planets and everything there is move, the bending they create in the fabric of our universe moves with them. And what is true locally around these objects may well also be true for the universe as a whole. In other words, even though he did not believe it himself, Einstein had found that our universe could change over time, that it could have a future. And if something has a future, it could also have a past, a history, and maybe even a beginning. Before Einstein, it was understood that our universe had always just been. Now we know that it hasn't, at least not in the way we experience it. And we've now known this for 100 years. So, as far as knowledge is concerned, the universe we live in, our universe, is 100 years old. 4 layers of pasts. Traveling through the known universe as you did in part 1 is a bit like strolling around a forest on your tropical island and being amazed by the beauty of the trees. After such a walk, you could of course go back to your villa, have your friends over for a drink and tell everyone how lovely it is out there, how good it felt to breathe the fresh oceanic air. But then, your friends could rightfully wonder why the trees grow, why their leaves are green, how all these plants came to be the way they are. If the universe is our forest, what is there to figure out about it? Instead of questioning the freshness of the shrimps you ate, what should those friends of yours have asked regarding the big picture? Beyond looking at it, is there anything to understand at all? And, seriously, is it actually possible to travel out there the way you did? To that last question, the answer is easy, with your body alone or in a spaceship, no. As far we know for now, it is not possible to travel through space and time like this any other way than in your mind. Nothing that carries any kind of information whatsoever is able to travel at a speed greater than the speed of light. So what your mind did in part 1 was to actually fly through a frozen 3D picture of the universe as it is known today, a reconstruction obtained by patching together all the pictures taken by all the telescopes that have ever been built on Earth. You may retort that you saw things move, that it wasn't a still picture. Fair enough. So let's say it was an almost frozen picture. Now, what can we make of it? Is there any law that governs the evolution of everything? The morning after your mind trip, when your friend who watched over you overnight left your villa to fetch some breakfast, you intuitively knew that she was still there somewhere, outside, even when you could not see her anymore. Didn't you? You did not start imagining that she had turned into smoke and traveled back in time to hunt a dinosaur and cook one of its legs before coming back for you to eat it. That would be rather cool, I agree, but just as it would be unwise to jump off a cliff or from a window, it is not going to happen. A fundamental reason why this won't ever happen is very tricky to state and prove, but we have to assume a few things if we are to try and unravel the mysteries of our universe. So, the first assumption, or postulate, we will make is this, that we are able, somehow, to understand nature even beyond what our senses can tell us. In order to do so, we shall henceforth assume that, under similar conditions, nature obeys the same laws everywhere in space and time, whether here or out there, whether now or in the past or in the future, whether we can see it or not, whether we know these laws or not. We shall call this our first cosmological principle. It is in bold letters because it is important. Were we not to assume it, we'd be completely stuck and unable to guess anything about what happens in places where we are not looking, or which are too far away from us, or too far back in time. If we don't make this assumption, then your friend might as well have been time traveling to hunt a yummy dinosaur. In fact, there are many hints that this first postulate is correct, at least within the universe we see through our telescopes. Take the sun. We know what particles, what frequencies of light, what types of energy come out of it. We detect them as they shoot out from its surface and land on Earth. So what about other, faraway stars? Do they shine thanks to the same kind of nuclear fusion reaction, or are they completely different? Are they like a burning log surrounded by fire, or are they made of plasma, like the sun? We don't have many tools at our disposal to probe such queries. In fact, we only really have one, the light we receive from these stars. In it is encrypted many of their secrets, and one of these secrets that we have been able to decipher is that the laws of physics are the same everywhere. So, since light is key to our understanding of the cosmos, let's have a look at what it is. Light, aka electromagnetic radiation, can be thought of both as a particle and as a wave. As you will see later, both descriptions not only work, they must both be taken into account if we wish to understand our world. For now, however, it is sufficient to just look at it as a wave. To describe waves in the ocean, you need to specify two things, their height and the distance between two consecutive crests. That height matters is obvious. You would be wise not to react in the same manner to, say, an approaching 50-meter high wave as to one that is just 2 millimeters high. The idea is the same with light, and the height of a wave of light gives what we call its intensity. Similarly, there is a difference between waves at sea that are hundreds of meters apart and waves that are very close together. That distance is called, rather appropriately, the wavelength. The longer the wavelength, the fewer the waves that arrive during a given time period, a number that is related to the wave's frequency. To intuitively feel that the shorter the wavelength, the higher the energy involved, you can picture yourself in front of a dam, whereas a 5-meter high wave hitting the dam once a month wouldn't be cause for you to worry, a similar wave hitting it 10 times per second would. For light, it is the same, the shorter the wavelength, the greater the energy carried by its wave. Now, contrary to what our ancestors thought, our eyes are light receivers, not light sources. And they are not built to detect all the types of light that exist, neither in intensity nor in wavelength. Too powerful a source purely and simply destroys your retina, blinding you in seconds. That is what happens if you stare at the sun, or at a laser, or any source of light that is too intense. We can only see waves of light that are not too intense nor too dim. The wavelength-related limitation of our eyes is more subtle. Over the millennia during which our ancestors evolved, their light-detecting organs adapted to see what they needed most to survive. To pick a fruit, or to be aware of the presence of a saber-toothed tiger, it was rather more useful to see the colors green, red or yellow than the X-rays emitted by falling stars near distant black holes. In short, our eyes have thus adapted to the light that is most necessary in everyday life. We would have become extinct long ago had we only been able to detect X-rays. In the end, then, what our eyes can see today is rather limited compared to all the existing natural types of light. But the universe doesn't care. It is filled with all of them. Appropriately again, we have called visible lights those lights we can see, and we've given individual groups of them some further names, colors. The distinction between one color and another can sometimes seem rather arbitrary, but a very precise mathematical definition exists, a definition based on a distance, their wavelength. It is true that some animals' eyes have evolved differently, that some can see lights that are slightly outside what we humans can detect. Snakes, for instance, have infrared vision, and some birds can detect ultraviolet lights, both beyond our human visual capabilities. 13 But no animal has ever built apparatuses to detect them all. Except us. And we've become quite good at it. From the least to the most energetic, the lights that surround us are radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays and gamma rays. Radio waves have very long wavelengths, 1 meter to 100,000 kilometers or more between each wave, whereas for gamma rays the wavelength is shorter than a billionth of a millimeter, but they are all light. And all the telescopes we have ever built have been engineered to harvest them, wherever they come from, whatever their intensity, to enable us to look at the universe through all the different windows our technologies allow. When you stare at the sky, whether it is with the naked eye or through some telescope, you therefore capture and process waves of light that have been emitted in outer space, somewhere, by a faraway source. As I said earlier, it was through a 3D reconstruction of all these images, recorded and reported, that you traveled in part 1. But what you may not have noticed back then is that, although it certainly was a journey through space, it was also a journey through the past, because light does not travel instantaneously. Now that is an interesting, if rather gloomy, question that your tropical island friends might have asked you. Haven't we all heard someone, somewhere, at a dinner party or elsewhere, trot out the line that the stars we see in the sky are actually all dead? Is it true? Are all the stars dead? Well, no, they're not. Not all of them, at least. Let's see. Let's assume that a great aunt of yours, a distant relative who loves to give ugly crystal vases to everyone at Christmas, lives in Sydney, Australia. Being slightly old-fashioned, she never sends any news to anyone, except for on her birthday, in January, when she mails everyone a picture of herself standing next to the mailbox she is about to slide the picture into. On the back of the postcard, she always writes, "It is my birthday today. Would love to hear your voice. Love from your auntie. P.S. I hope you liked the vase I sent you." The problem is that even though you promise yourself, every year, to think about her, you don't, and, as always, by the time you receive the postcard it is not today for her anymore. It may not even still be January. As usual, you hope she hasn't been sitting by the phone all that time, waiting. In any case, what is important in this story is that the picture she took of herself a minute before mailing the card, the picture you are now holding in your hands, is unlikely to still correspond to what she looks like now. She may even be dead, for all you know, like some of those stars up there in the sky. Now don't worry, your great-aunt is sound, you'll get a few more vases, and you'll be able to have a few more goes at getting her to use email instead of postcards. That would certainly be quicker. But it wouldn't be instantaneous. Nothing is. With email, you'd still get her picture a fraction of a second after it was sent. So once again, she might be dead by the time you receive it. The idea here is not to make you paranoid that everybody you know might be dead. Rather, it is to show what happens in space, where the quickest delivery service possible uses light as a communication device. And light, however fast, is very far from traveling instantaneously. In outer space, its unrivaled speed reaches a staggering 299,792.458 kilometers per second. Light can travel about 26 times around the Earth while you read this sentence. It is fast, the fastest thing there is, but amazingly slow considering the intergalactic distances involved out there. Now, anytime a star shines, its light carries an image of itself. That image shoots through space at the speed of light, and it can take a very long time to reach us. This means that yes, the furthest stars we see in the sky are probably dead. But not all the stars. The Sun, for one, isn't. To be more precise, right now no one knows, but the Sun wasn't dead 8 minutes and 20 seconds ago. As you saw in part 1, the light from the Sun takes about 8 minutes and 20 seconds to travel the 150 million kilometers that separate us from it. This means that if the Sun was to stop shining now, we'd know about that problem in 8 minutes and 20 seconds. It also means that, from the Earth, you will always see the Sun as it was 8 minutes and 20 seconds ago. Never as it is now. The Sun that shines in the sky on a sunny day never really is as you see it when you see it. It isn't even where you see it anymore. During the 8 minutes and 20 seconds its light takes to reach your skin, the Sun moves by about 117,300 kilometers on its own orbit around the center of our galaxy. Now, the furthest light that we have managed to detect in our universe has traveled for as much as 13.8 billion years before hitting our telescopes, straight from when the universe became transparent. The huge stars that started shining a few 100 million years after that most certainly do not exist anymore, even though their light reaches us now, making them visible to us. The same can be said for many other stars between the Sun and those far reaches of our universe. On January 24, 2014, for instance, astronomers saw a star explode in the night sky in a faraway galaxy. They saw it live, as the light from the explosion reached their telescope. As far as we're concerned, that star therefore died on January 24, 2014. But anyone living next to it would have witnessed the explosion as it unfolded there, 12 million years ago. To summarize, if we wish to probe space from Earth, modern technologies do not leave us much choice, we need to use light. No one can travel to the other side of the universe. No one can teleport there instantaneously. In the end, just like the visible universe that you traveled through in part 1, looking at the night sky is like receiving individual picture postcards from everywhere, all stamped at various times and locations in the past history of our universe, according to when and where they started their journey. Only by patching together all these postcards from the edge of forever can we reconstruct a slice of the history of this universe of ours, as it is seen from Earth. It is through such a slice that you traveled in part 1. 5. Expansion. To repeat, everything we know about the faraway universe comes from the light that reaches us. To decipher it, to understand it, we therefore need to figure out exactly what information light carries, and how it interacts with the matter and its building blocks, the atoms that it meets in space. You will plunge right into the heart of atoms in the part after next of this book, but, for now, you do not need to know everything about them. Let's just say that atoms can be described as round nuclei surrounded by swirling electrons, and that these electrons aren't randomly scattered, but rather organized in layers around the nucleus. It might be tempting to picture them as planets whirling around a central star, but that would be misleading. In fact, we call the trajectories of electrons around their atomic core orbitals expressly to distinguish them from planetary orbits. Given the right speed, a planet can theoretically orbit its star at any distance it likes, but this is most certainly not the case with electrons. Contrary to planetary orbits, electronic orbitals are separated by electronic no-go zones, places where electrons simply can't be. Moreover, the electrons can also easily, spontaneously, even jump over these forbidden areas, from one orbital to another. However, and here is the key point, such jumps do not happen for free. To move from one orbital to another, electrons have to either absorb or emit some energy. And since it so happens that the further away from an atom's nucleus an electron is, the greater the energy it carries. For an electron to jump from one orbital to another further away, it has to gain some energy, a bit like a blast of flame gives a hot air balloon a lift. Conversely, to move closer to a nucleus, an electron has to emit something, to get rid of some of its energy, like a balloon venting hot air in order to drift back to Earth. But where does this energy come from? Well, that is where light comes in. Electrons can jump from one orbital to another by absorbing or emitting some light. But not just any light. To get from one orbital to another requires electrons to jump over the electronic no-go zones that separate them, and achieving such a feat involves swallowing, or giving away, a specific amount of energy, corresponding to a specific light ray. Were they to be hit by some light that is not quite energetic enough,